Hey everyone, welcome to this explainer. So, you know that feeling when you're staring at a rack of blinking lights or a massive tangled mess of cables, and you just kind of wonder what on earth is actually happening back there? Well, you are absolutely in the right place. Today, we're going to untangle the alphabet soup of networking hardware. It's like a giant puzzle, and we're going to build a network from the physical cables all the way up to the cloud.
All right, here is our game plan for today. We'll start with the typical network setup, dive into Layer 1's physical foundations, and then explore Layer 2's local network traffic. After that, we'll hit Layer 3 and network security, talk about modulators and demodulators, and finally, wrap things up with a head-to-head switch versus router comparison. Let's dive right in.
Kicking things off with Section 1, the typical network setup.
So to understand the individual components, we really need to picture the big picture first. Think of our end goal today. Down at the bottom of a network, we've got our everyday end devices, PCs, laptops, and smartphones, connecting into access points and switches. From there, that traffic connects up to routers, passes through firewalls, hits a modem, and ultimately traverses out to the vast internet. By the end of this, we want to completely understand every single box in this chain. So let's start at the very bottom.
Moving right along to Section 2, Layer 1, the physical foundations.
Right at the absolute base of the OSI model is Layer 1. This is where devices literally have zero intelligence. They only understand raw physical, electrical, or optical signals. The most basic device you'll find here is the repeater. Why do we need it? Well, standard Ethernet cables actually max out at about 100 meters. That's roughly the length of a football field. Go beyond that, and the electrical signal just degrades. A repeater doesn't read addresses, it doesn't filter traffic. It basically just catches a weak, exhausted signal and gives it a pure physical boost.
It's actually really cool to think about this physical process happening in real time. Just imagine a weak, degraded wave coming in from a source device. The repeater grabs that tired signal, perfectly regenerates it back into a strong, clean electrical wave, and just sends it right on its way for another 100 meters. It's pure signal regeneration, plain and simple.
But what if you need to connect more than just two computers? Well, if you take a repeater and give it a bunch of ports, you get a hub. Now, a hub is a legacy Layer 1 device, and frankly, it has no brain. When one PC sends a frame of data in, the hub just blindly floods that data out of every single other port. It's kind of a mess. It creates this single shared collision domain where all the devices are just constantly competing for bandwidth. If two devices try to talk at the exact same time, their signals literally physically collide.
Which brings us to Section 3, Layer 2, focusing on local network traffic.
So to solve that massive collision problem, we have to move up a layer and introduce some basic intelligence to our local network. And to even participate in a Layer 2 network, a device needs a network interface card, or a NIC. Whether that's a hardwired gigabit Ethernet card plugging into a motherboard or a wireless adapter, the NIC provides the physical connection. But most importantly, it securely stores a unique 48-bit hexadecimal MAC address. Think of this as a permanent digital fingerprint that's hard-coded right in there by the manufacturer.
Now that our devices actually have these unique fingerprints, we can upgrade to a switch. The concept of a switch brilliantly explains why it completely replaced the hub. When one PC wants to talk to another, the switch doesn't just blindly flood the network. No way. Instead, it looks up the destination MAC address in its own internal MAC table. It sees exactly which port that specific address is on and forwards the data exclusively to that port. Because of this intelligence, every single port gets its own separate collision domain, which drastically speeds things up.
Similarly, operating right there at Layer 2, we have the bridge. A bridge essentially connects two separate network segments together. Kind of like a switch, it learns the MAC addresses on both sides, but it acts as a really smart filter. If a PC on one segment wants to talk to another PC on that exact same segment, the bridge smartly drops or filters that local traffic so it doesn't clog up the other side. It only forwards frames that actually need to cross over to the other segment.
Finally, for Layer 2, we have the access point, or AP. This is what brings us into the wireless world. An access point is basically a wireless bridge. It seamlessly links your smartphones, tablets, and laptops using Wi-Fi radio signals directly into your hardwired Ethernet LAN. The AP isn't routing the traffic itself. It's literally just bridging the invisible wireless frames and the physical wired network.
All right, moving on to Section 4, Layer 3, and network security. Okay, so we've got our local devices communicating smoothly. But how do we actually reach the internet and stay secure while doing it? Well, the crucial point here is the transition between two very different types of addresses.
In Layer 2, we relied on MAC addresses, those permanent physical identifiers for local delivery. But the internet is massive. We can't possibly memorize the physical fingerprint of every single device on Earth. So, moving into Layer 3, we introduce IP addresses. These are logical hierarchical addresses designed specifically to help us navigate and route traffic across vast, totally different global networks. And this is exactly where the router steps onto the stage. The router is a highly intelligent Layer 3 device. It doesn't look at local MAC addresses to make its primary decisions. It uses those logical IP addresses. By checking its internal routing tables, a router figures out the absolute best path for your data to travel outward across the world. And crucially, routers also stop local broadcast traffic from leaking out, which completely isolates different networks from one another. Now, if we move even higher up the OSI model, we run into gateways and firewalls. Think of a gateway like a funnel. It's basically the ultimate network translator. It converts completely different protocol architectures, like taking standard TCP IP traffic and translating it into a voice-over IP phone signal. Firewalls, on the other hand, act as rigorous security guards. Operating from Layer 3 up to Layer 7, they enforce strict access control rules, inspecting packets to build a solid protective brick wall between your trusted internal network and the completely untrusted outside world.
Next up is Section 5, Modulators and Demodulators.
But wait, before our digital data can actually travel across those physical external telephone or coaxial cable lines outside your house, it requires a physical translation. Enter the modem. Fun fact, that's actually a mashup of the words modulator and demodulator. It executes two essential steps. Step 1 is modulation, taking the digital blocks of zeros and ones generated by your computer and translating them into analog waves for the transmission line. Step 2 is demodulation, taking those returning analog signals and converting them right back into the crisp digital zeros and ones that your local network can actually process.
Let's wrap things up with Section 6, a switch versus router comparison.
To make absolutely sure we've locked down these concepts, let's look at a meticulous side-by-side comparison of the two biggest heavy hitters we've discussed. Think about how a switch operates strictly at Layer 2, relying on physical MAC addresses and an internal CAM table to connect devices within the exact same local area network. A router, however, operates at Layer 3. It utilizes logical IP addresses and complex routing tables to connect entirely different networks together.
Furthermore, let's look at their scope of isolation. A switch generally creates just one large broadcast domain, meaning if one device shouts, everyone else on that switch hears it. But a router, it actually separates those broadcast domains entirely. And because the router acts as the gateway to the outside world, it takes on a lot of heavy lifting that a standard switch just doesn't do. We're talking things like network address translation, assigning IPs via DHCP, and choosing the optimal path across the global internet.
So we've successfully built our network from the humble repeater all the way up to intelligent gateways and routers. Now that you understand exactly what each of these 10 distinct components does under the hood, I want to leave you with this provocative thought. Today, the basic Wi-Fi box sitting in your house is likely a combined modem, router, firewall, switch, and access point all rolled into one. As technology rapidly consolidates all these specialized functions into single, invisible black boxes, which distinct hardware device do you think will be the next to vanish entirely into the background? It's definitely something to think about. Thanks so much for joining me on this explainer, and keep questioning the technology that connects us all.